Welcome! In this video I'll show you how to solve problem 2.4 as it appears in the 4th edition of Griffiths Introduction to Electrodynamics. Now this problem states the following. It says find the electric field at distance z above the center of a square loop of side A carrying uniform line charge lambda, right? And they tell us to use our previous result. However, that is a little bit too easy. We don't like easy. Here we do things the right way. I'm going to just solve it all at once, and you can just, skip ahead if you want. I'm just going to solve it, and you will see how much of this you want to watch. Okay, so step number 1, as always, find and define our coordinate system. This is the order that I always like to use. So we define our coordinate system. Now, in this case, because of the symmetry of the problem, of course, we want to have our 0 here right underneath our point, right where this point there is. And I would define x maybe in this direction. Now we are in 3D, so y would go in that direction, right? So this here goes through y, this here goes through x, and z goes up here, right? So this vertical distance there is z. I know that I'm not the best artist, but I hope that you can understand it. Okay, so that is our coordinate system. And now, what exactly is it that we want to do? So what we now want to do, because in 3 dimensions it can be a little bit tricky, we want to find the contribution of this line segment, and we will use the fact that we will use the superposition principle. So we will find this line segment, this line segment, this line segment, and this line segment. Now, fortunately, because of the symmetry of the problem, if we find one, we already found all of them, because this is a square. So the length of them are all the same. The line charge is all the same. They're just going in different directions, but their distance is also the same, right? The distance from this is always the same as this, and as this, and as this, right? So the distance to this point is the same as the distance from this point, for example. Okay, so just choose whichever one of these you like the most. Maybe we can take this one because it's the one that is like the most similar to what we have seen in the past. So if we take this one, then let's go to step 2, which is, as usual, to write down the electric field formula, and we will see what we know and what we don't know. Well, and it's going to be quite similar to the past few cases. So 4 pi epsilon 0, we integrate, right, because we don't have a point charge, we have a distribution. We integrate over the charge density, and we go along the line. And of course, we have to consider our position vector, right? That is the direction in which the electric field will be pointing, and we divide by the magnitude of our vector squared. Now, as usual, I like to use the r hat notation. If you like to use the r vector notation, in which case you would have r vector divided by the magnitude cubed. I mean, yeah, then you do you. Be happy. It's the same. It's the exact same thing. Okay, so now let's go for our r hat vector. Let's try to find it, right? That's the 3rd step, right? Now find our unknown r hat. So how do we do this? Well, if we have any dl, so let's say that this is our point of interest or our segment of interest dl, right? Then the vector from this to our point is going to be exactly that one, right? This right there is going to be our r vector. So how do we find it, right? How exactly is it that we can find that vector right there? Well, fortunately, this is where we can apply the beautiful method of simply walking, right? How do I go from this position all the way to that position? So to go from here to our point P, first of all, we need to move along the x-axis, right? We need to move in this case, the positive x-axis. If we are on this side, we're going to go into the negative side. So if we are, for example, at -5, then we need to walk 5, but in the positive direction. If we are, for example, here, which would be at, I don't know, 5, just to put some numbers there, then we would have to go -5. So basically, we need to go minus the amount in which we already are. So if we are at x, we need to walk minus x in the x direction, right? So if we are at 2, we need to walk -2 to get to 0. And if we are at -2, we need to walk -2, which is 2. All right? So let's write down our R vector here. So R vector is, first we walk -x step in the x hat direction, and then we need to walk from here to the 0 point, which means we need to walk this distance, which is half of the entire distance. So this would be a over 2. So we need to walk a over 2 steps in the y direction. And from there, we need to go from the center all the way to point P, which is z in the z direction. So that is, I think, the easiest way to finding the R vector. Okay, now what is the magnitude of this vector? Well, that is simply Pythagoras' theorem, but extended to 3 dimensions. So the magnitude of this vector is the square root of this thing squared plus this thing squared plus this thing squared. All right, so that's x squared plus a over 2 squared plus z squared. Okay, and thus, of course, the R hat vector, the unit vector, is simply R vector divided by its magnitude. So now we can plug all of this into our equation for the electric field. So the electric field let's say electric field 1, right? Because this is due to this one line there. So the electric field due to this first line, let's say this is 1, 2, 3, and 4. So the electric field due to 1 is going to be 1 over 4 pi epsilon 0. And then we integrate. Now, what are the limits of our integral? If we are integrating over this line, then of course our dl will simply be dx. And our lower limit will be x equal minus a over 2. And the upper limit will be a over 2. So we integrate from minus a over 2 to a over 2. Okay, now we have a lambda, the R hat vector, which will be minus x hat plus a over 2 y hat plus z hat, and all of this divided by x squared plus a over 2 squared plus z squared. Okay, and all of this dx, right? Did I forget about anything? Oh yeah, this is the square root, but we still have to cube this, right? Because we get this thing squared just because of this part, and then we have to multiply once again because of the R hat vector, right? We get 1 and then 2, 3. Okay, that's why it is cubed, as usual. Okay, so now we need to integrate this, and notice that this is going to be quite similar to what we have done many times in the past. All of this part doesn't depend on x, only this part depends on x. So let's now separate this integral. So we get lambda divided by 4 pi epsilon 0. And then we integrate, actually, let's separate this as I said. Okay, let's separate it before doing this. So first, the part that does have things that depend on x. So we take minus x hat out of the integral, again, x hat. This is simply a constant vector. It is 1, 0, 0. So it doesn't depend on x. So it is not affected by an integral in the x direction. So this is from minus a over 2 to a over 2. And then we still have x dx divided by the square root of x squared plus a over 2 squared plus z squared. And this thing, of course, is cubed. Now, I do prefer to write it like this. So instead of having the square root, I do like to say this is to the 3/2 because it makes integrating easier. It makes it easier to see what's going on, at least for me. Okay, so then we have the integral of all the things that do not include an x. So a½ in the y direction plus z in the z direction. And then we integrate from minus a over 2 to a over 2 of dx and divided by the same thing as before. So x squared plus a over 2 squared plus z squared to the 3/2. Okay, so these are the two integrals that we need to solve. It's the exact same that we have solved a few times, but of course I will show you once again how to solve them. So to solve that integral, well, first of all, let's separate it. So this will be I1 and this here will be I2. All right, so we will solve them separately. So let's begin with I1. So this integral, this is integral from minus a over 2 to a over 2, just writing it down to make sure that it is as clear as possible, right? I do not want any confusion because learning to do this integral is very important. It appears very often, as you see. So how do we integrate this? This looks nasty. Well, don't be scared. Whenever we have in our denominator here something that its derivative is in the numerator, this is telling you try to use substitution. Because if we use a substitution that involves x squared, then the du will simply be x dx, in this case, of course, times 2. And that is precisely what we have here, except for the 2 factor. But we can see that du divided by 2 is precisely x dx. So that is why we want to use a substitution that is x squared plus all these constants, right? Of course, z is a variable, but not with respect to x. It doesn't change as x changes. It is independent. So that is why if we take the derivative with respect to x, z doesn't change. All right, so that means that we can now do the following. So we have a new integral. I will not change the limits because I am lazy. When I am done with integration, I will just plug it back in, but I will not do it right away. So here we have x dx, which we know is 1/2 of du. And then in the denominator, we have u to the 3/2. And look at how this just became so much easier. We know how to solve this. This is simply the integral of u to the minus 3/2. So that is, of course, let's see, 1/2. And the integral of this is going to be minus 2u to the minus 1/2. You take the derivative, you get minus 1/2, which cancels out this, and you get u to the minus 1/2 minus 1, which is minus 3/2. All right, so now we have to undo our substitution. This and this cancel out. We get minus 1 over the square root of x squared plus a over 2 squared plus z squared. Okay, and now we evaluate this at our endpoint, so minus a over 2 and a over 2. Okay, so at a over 2, we get minus 1 divided by, and now we get a over 2 squared plus a over 2 squared. Now, each one of those is a squared divided by 4, so we get a squared plus a squared, which is 2a squared, so we get a squared divided by 2. So this thing is a squared divided by 2. All of this inside the square root, by the way. And then we have plus z squared. And then we have minus, right? 1 from here. I mean, 1 that was already there, and 1 from evaluating at minus a over 2. So then you have 1 over, and now we plug in minus a over 2. But since it's squared, the minus cancels out, and we get the exact same thing. So we get a squared over 2 plus z squared, and this becomes positive. And will you look at that? It cancels out. There we go. Could we have seen this coming? Yes, we could have. Why? Because this integral is odd, right? It is an odd function, right? This part is even in x squared. This part is odd, and it is in a symmetric interval. So if we had seen that, we could have seen this coming and gotten that it's 0 anyways. I just want to show you how to solve this integral because it's a fun integral, and it's not always 0. There are cases where it's like between 0 and a or something like that, and in that case, it's not going to be 0, so it is good that you know how to integrate. Okay, now, let me just get rid of this. There we go. And now we'll go into our next integral, which is I2. So, wait, I just deleted the result. It was 0. Okay, never mind. I panicked for a moment. So this entire part is 0. And this, of course, makes sense because we are in a situation that is symmetric, right? So if we look at our drawing, if a point in the left half is pushing it to the right, there is an exact amount on the right pushing it to the left, which is why they cancel out. All right, so it makes a lot of sense for that part to be 0. Now, what about this second part, I2? So I2 is integral between minus a over 2 and a over 2 of dx over x squared plus a over 2 squared plus z squared to the 3/2. Now, we have seen how to solve these in the past as well. Now, just in case you're wondering, this is an even function over a symmetric interval, so you could write this as twice the integral from 0 to a over 2 if you're interested, but it doesn't really simplify things all that much, so I don't really care in this point. There are some times when something like that is useful, but here it doesn't do too much. Okay, how to solve an integral like this? Whenever you see that in the denominator you have x squared plus a constant, you can almost always go to x squared plus 1, right? Or perhaps instead of x, rather u squared, a different variable. And whenever you have something like u squared plus 1, you can use another substitution to go to tangent squared of theta plus 1. And we know that that thing is the secant squared of theta. So instead of having something summing, you simply have secant, which means that you can apply this exponent and you are already in a much better situation. Also because the derivative of the tangent, which will come out in dx, is the secant as well. So that is the logic behind it. Okay, so whenever you have this x squared plus something in the denominator, think of tangent. And if you have like a minus, you can think cosines, sines, and try to find something there. Okay, so first we need to transform this into something like that looks like this. So for that, we need to factor out that thing right there. So this is integral from minus a over 2 to a over 2 of dx. And now let me factor out that. So we factor out a over 2 squared plus z squared, and all of this is to the 3/2 power. And then we have x squared divided by, all right, and then we have, whoops, a over 2 squared plus z squared. And let's see, then we have plus 1, right? Let's double check. If we, and this is to the 3/2. If we were to multiply, this would cancel this part out and it goes back there. There we go. Okay, so now we factor it out. And of course, that thing is a constant, so it can just go right outside of our integral. So a squared plus z squared to the 3/2 power. And then we have the integral of minus a over 2 to a over 2 of dx. And now look at this, x squared. Now this may not look all that nice, but it is what we wanted. This is a over 2 squared plus z squared. And this is basically a number. It may as well just be 2, right? Because it's for a fixed value of z. So 3/2. So now we can just say, okay, this is the quick way to do it. You can do either an intermediate step and say u is equal to x divided by the square root of what we have underneath. So a squared plus z squared. Okay, and why does it have to be the square root? Because we want this thing to be squared, right? We want that to be u squared. So for that to be u squared, we need to take the square root of this. So square root of x squared is x, and we need to take the square root of that. Okay, so you can do that so that you end up with u squared plus 1, and then you can apply the tangent. I will do this right away. I will say, let tangent of theta equal to x divided by the square root of a over 2 squared plus z squared. All right, and again, I will not worry about the limits of integration. I will just come back to it at the end. So here dx will thus be the square root, right? I'm just multiplying through here so that I can just plug it in, times the secant squared of theta d theta. Whoops, I missed the c. Secant, okay, again, secant squared of theta d theta. Okay, so now let's plug it in. So plugging this in, changing colors, we have 1 over a over 2 squared plus z squared to the 3/2 indefinite integral of dx, which is the square root of a over 2 squared plus z squared. And then we have secant squared of theta d theta divided by, and now we have tangent squared of theta plus 1 to the 3/2. And notice now that this part cancels out the square root down here. So instead of having 3/2, you end up with 1. So this is now to the 1 power, which is very nice. And this thing, tangent squared plus 1, is secant squared, right? That is a very important trigonometric identity that you need to know. I cannot emphasize it enough. Okay, because this is a very common integral that you may encounter. Okay, so this thing here, tangent square of theta plus 1, is simply secant squared, right? So this is secant squared of theta, but you have the square root right there. So instead of secant squared, it is now secant. But now you have secant squared divided by secant cubed. So you end up with simply 1 over secant. But what is 1 over secant? Well, secant is 1 over cosine. So 1 over secant is 1 over cosine, or simply cosine theta. All right, so we simply need to now integrate cosine theta, which will give us sine theta. So we get 1 over a over 2 squared plus z squared, and then we have sine theta. All right, now we need to undo our substitutions. So we knew that tangent of theta is this thing. So that implies, and this is the trick that you need to use whenever you want to undo this trigonometric substitution. The tangent theta implies the existence of a right triangle where an angle theta is here and the opposite side is x. The adjacent side is, oh, this is nasty. The adjacent side is square root of a over 2 squared plus z squared, and the hypotenuse is this thing squared, so a over 2 squared plus z squared plus x squared. All right, so that is, and thus the sine of this, right, the sine theta would be this part divided by that part. So let's just write it here directly. So that would be x divided by the square root of a over 2 squared plus z squared plus x squared. Okay, so that is the result of this integral. Of course, we still need to evaluate between minus a over 2 and a over 2. Okay, so if we do this, let's see. So if we evaluate at a over 2, we get a over 2 divided by a over 2 squared plus z squared, and then times 1 over the square root of a over 2 squared plus z squared plus, and now a squared divided by 2, so a over a half squared. But of course we also have this a squared there, so we end up just as before with a squared divided by 2, right? This is 2 times a squared divided by 4. Okay, so that is from the first part, and then we have to do minus a over 2 divided by the exact same thing. So we end up with minus, they cancel out, with plus a over 2. So basically we are adding the same thing twice, as we saw before, because it's an even function in this symmetric interval. So we end up with twice this result. So 2 times a over 2, which is simply a. Okay, now let me copy this result and plug it into our original equation here. Okay, so this would be, let's see, a divided by a over 2 squared plus z squared times 1 over the square root of a squared divided by 2 plus z squared. All right, and this is, of course, I'm going to move this around a little bit. just so that there isn't that like huge gap that we got because the other part was 0. All right. So there we go. This is the result for y and z directions. And this is for the first one. Now we have to do this 3 more times, but actually we don't really have to do it because the integration is the exact same thing. And notice that in this part, the x component canceled out, right? And we got a little bit in the y direction. But notice that if we do the same thing, but now for this line that I'm drawing in red, it's going to get a component in the y direction that exactly cancels out what we just got. So the y component, right, when we are getting the total electric field, this y component will cancel out because the other one will give us the same result, but with minus a over 2. How do I know it? In fact, if you want to check, you can write down the r vector for this part. So for that part, right, let's say r2, maybe this is r1, the r2 vector, right, if you are here, well, you need to move, first of all, this is minus x, right, same as before, so you need to move minus x, x hat, then you need to move this distance, so you need to move minus a over 2 in the y direction, and well, still z in the z direction. So this component is the one that cancels out this component, while the x integral will cancel itself out because you're integrating over a symmetric interval. And similarly, if we do, for example, actually I called this 2, but I had called it 3 before, so I'm sorry, this is 3. If now we do R2, right? Now thinking of, let me get rid of some of these things, of now this right segment. So if we want to do this one, what would the vector be? Well, if we are somewhere over there, for example, we would need to move minus y in the y direction, and then you need to move this distance right there, which is a over 2, but in the negative x direction. So minus a over 2 in the x direction plus z in the z direction. And if you now go for R4, for example, then let's say that you are maybe there, you still need to move this minus y hat, but then you need to move plus a over 2 x hat plus z hat. So once you do the integrals, right, the only thing that changes from all of these are these r vectors, right? So this is the part that's going to cancel out because of symmetry. If you're integrating this segment there, everything that is on that side will cancel out everything on this side, right? Which is exactly what we saw at this minus x hat previously. And then the contributions from x here will cancel out just as the contribution from from y canceled out before. So in the end, all that we get is the z component here, 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 and here. Of course, you could have found this out much earlier if you had seen this problem and said, all right, we only need to find the z components. But in the end, the work would have been basically the same, right? You would have gotten to this integral, except that this and this would have already been 0, and you just would have to solve this one integral, which is the one that we solved down here, right? So I just like to teach you the intuitive way, basically, or just the just going through it way, which is what we just did, and also thinking about it, because sometimes you don't notice things. Okay, so the total field in the end, so the total electric field is going to be 4 times this electric field that we found in the z direction, right? So this part here is going to cancel out in the end. All right, so only in the z direction, of course. So maybe let's say E1z. Okay, so this would be lambda divided by 4 pi epsilon 0. And then we have, is there any orderly way to do this? This is z times a, this is 4, so 4 lambda z a, and then we have to divide by a over 2 squared plus z squared times the square root of a squared over 2 plus z squared. And this is, of course, in the z direction. So there we go. This is the total electric field that we were looking for. So as you can see, the procedure is relatively simple, right? We just need to write down this R vector. If we have multiple segments, we write them down, and it is usually important to see if there is any sort of symmetry, because if we can't save ourselves any sort of trouble, for example, if you had not noticed that all four vectors will give you basically the same integral and that they cancel each other out. I mean, imagine doing this 4 times. You really don't want to do that. So always keep an eye open for symmetry in these problems. So there it is. That is problem 2.4. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.